Today we're going to do an overview of three chapters. The respiratory chapter, which would be chapter 14, the urinary chapter, which is chapter 16, and acid-base, which is chapter 17. And of course, those are referring to your textbook. You can use your textbook and also the online McKinley second edition, which you can access through your Blackboard. So let's start out with the respiratory system.
Oh, start that again?
Start over?
Intro? Yeah.
Okay.
Just that intro.
Okay. Say when.
Okay, good.
Today we're going to do an overview for Bio 169 of three systems. So the respiratory system, which is chapter 14, the urinary system, which is chapter 16, and acid-base, which is chapter 17. Everything I'm talking about really refers to the textbook with those chapters, and then you can always go to your Blackboard with the McGraw-Hill materials, and you'll see McKinley's second edition, which has all the PowerPoints and any additional material or information that you should need for this course. So the first thing we're going to do today is start off then with the respiratory system. And of course, respiration is really based on the concept of the word of one respiration equals one inspiration plus one expiration. And those terms are really based upon the concept of respiration, which really has been replaced several years ago by using the word ventilation. So we used to call something a respirator, now we call it a ventilator. And let's first of all, to understand that, think about the three gases of respiration. The three gases of respiration are going to look at two different numbers. One is going to be inspired air. And inspired air we're going to think of as room air. And then we're going to think of expired air. And those three gases are going to be O2, CO2, and N2. Oxygen, which we're going to consider to be the nutrient gas, CO2 considered to be the waste gas, and N2 or nitrogen, the inert gas. In inspired air, we're going to kind of bring in approximately 21% oxygen, and we're going to expire out approximately 16%. The waste gas, we're going to have approximately, in the ambient air of inspired air, approximately 0.03%. We're going to expire out approximately 4%. And then nitrogen, which is our inert gas, is going to be approximately 78% coming in and 78% going out. And of course, there are some other small amounts of other gases, but they're not really significant for this course. The only time nitrogen would be an issue would really be what I would call deep sea diving or deep sea physiology. And that's why if we got into detail with that, we would think of deep sea physiology be something called the bends, also known as nitrogen narcosis. And I always think the best way to think of the bends or nitrogen narcosis would basically be if you were to take a bottle of soda, and if you look at that bottle of soda, and I can just give you an example here, I've got sitting right here a bottle of Coke. And as I can see, it looks like there's Coca-Cola up to here, soda, and I notice that there's a free airspace up above it. And I know that the company, when they produce this, in order to give you what's called the fizz, they put carbon dioxide in there. But for our example, we're going to think of nitrogen for that. So if I was to take this bottle and open it up right now, you would see that it would have a little bit of air being released from it. But again, I don't see any bubbles whatsoever. But if I take and shake this bottle, all of a sudden the bottle is totally filled up with gas. So that tells me that in the Coca-Cola or any soda, any carbonated beverage, the carbon dioxide was dissolved in the solution. In the human body, that nitrogen is dissolved in the solution. When that nitrogen then would bubble out, it would be released when you're doing deep sea diving, and therefore that's why you have these little air emboli causing something called the bends or nitrogen narcosis, which can be fatal unless you're treated in a hyperbaric treatment chamber. So that's just kind of the quick concept of always how you can think about how nitrogen is significant, or think about all of these gases are actually inside of my blood. So don't think of these gases as being, once they're inside of the body, as being these air bubbles floating around. They're actually dissolved in the plasma. So again, 3 gases of respiration. And then we also have to think about the 3 pressures of respiration. And those 3 pressures of respiration are going to be, number 1, ATM, which equals atmospheric. The second is going to be intra. Remember, intra means within. Intrapulmonary, which is also called intraalveolar. And then the third pressure of intrapleural. So again, 3 gases of respiration, 3 pressures of respiration. Let's just very simply understand what those 3 pressures of respiration are. At the same time, we can really learn what I would call the anatomy, or the gross anatomy of the lung. If we look at a lung, we know that the lung itself, and I'm just going to look at one right now, is going to be sitting inside of the cavity, the thoracic cavity, which is then subdivided into a pleural cavity. And then I'm going to have a tube coming into that. So if we said, what's this tube? That would be my primary bronchus. That's bringing air in and bringing air out. And the air that's being brought in would be ATM. So the air that comes in here is ATM, or atmospheric air pressure. So that's our first pressure of respiration. And then you notice as the air enters the lung, each lung is going to have literally millions of these air sacs. So this is going to be an alveolus, or an air sac. And the pressure inside of that air sac, as well as the pressure inside of that lung, because it's literally a solid mass of tissue if you were to look at one when it's deflated. That pressure is actually going to be the intrapulmonary, or the intraalveolar. And then we've got a third pressure. Well, that's going to be because my lungs are sitting inside my thoracic cavity. and then it's subdivided into the pleural cavities. So the lining of my thoracic cavity is called the parietal pleura. And the covering of the lung is the visceral pleura. And therefore, the space in between the two is going to be called the intrapleural space. And therefore, that's going to give me my third pressure of respiration, which is again my intrapleural pressure. So, again, if you look at this, if we were to say atmospheric air pressure, we would say would be pressure number 1. The second air pressure would be the one inside of the lung itself. So that's pressure number 2, intrapulmonary alveolar. And then the pressure between the pleura is going to be pressure number 3, or intrapleural. So understanding that, let's just think of the analogy of a lung compared to a room. And so kind of think of the room that you're in right now. So if I just say that this is my lung sitting here, here's my 2 lungs. My 2 lungs are sitting on top of the diaphragm. Think of the diaphragm equals the agonist or prime mover for respiration. Think of that diaphragm as really being the floor of the room you're in right now. So again, just think of this diaphragm as the floor of the room you're in. If you're looking inside of that room, pretend that that room is actually inside of the lung. So inside of my lung is literally going to be this alveolus inside of the lung itself. And so just think of that as being the interior of the room. And if you were to literally look up, you'll notice that no matter what kind of building you're in, or this room, there's actually going to be 2 what I would call roofs or ceiling. There's the ceiling that you're looking up at, and therefore that's going to be the visceral pleura. So that's going to be the ceiling of the room. And then above the ceiling in the room you're in, and that's again the parietal pleura, and think of that as being the roof of the building. And so the space between the ceiling and the roof of the building is going to be that intrapleural space. So thinking of those 3 pressures again, I know that I've got air coming into this lung through this bronchus. So here's this bronchus coming in with that pressure of ATM, or pressure number 1. I know that there's this pressure inside of the lung itself, and that's going to be pressure number 2. And then I know there's that pressure between the pleura, and that's pressure number 3. Now, the way you can really test yourself to see if you really understand that is ask yourself, what's the greatest pressure of inspiration? So what's the greatest pressure, P for pressure, of inspiration, going from highest to lowest? And the same question is, what's the greatest pressure of expiration, going from highest to lowest? Well, let's see. If I want air to come into the window of that room. So this bronchus up here coming in, that we've already called in the little diagram above the primary bronchus, that pressure coming in that room, just think of it as being the window or the door to that room. So the greatest pressure, if I want to bring air into my lung, that means that the greatest pressure to go in, always think of pressure moves from higher to lower. When gases diffuse, they go from higher to lower. So therefore, the greatest pressure of inspiration means that pressure number 1, which is ATM, atmospheric air pressure, is going to have to be greater than the pressure in the lung, which is greater than pressure number 2, which is intrapulmonary or intraalveolar. And that is going to have to be greater than pressure number 3, which is intrapleural. Now, for air to come in, the pressure coming through that door, atmospheric, has got to be pressure greater than the pressure inside of the lung, which is going to be intrapulmonary, intraalveolar, which is going to have to be greater than the pressure between the ceiling of the room and the roof of the building, and that's going to be intrapleural. If I want now the air to go out, a lot of people look at and they'll say, well, if it's 1, 2, 3 going in, it's going to be 3, 2, 1 going out. And the answer is that's incorrect. The reason being is that pressure number 2, so pressure number 3, which is called intrapleural, is normally a negative pressure. It means it's negative as compared to the other 2. That's what literally keeps my lungs from collapsing. So in order for that to work, and looking at this question of what's greatest when I expire air, well, the greatest pressure going out is going to be pressure number 2. So therefore, to get air out, the intrapulmonary or intraalveolar is going to have to be greater than pressure number 1, which is going to be atmospheric, and that's going to be greater than pressure number 3, which is intrapleural. So now we know basically how the lungs work. We know how the pressures, so we know the 3 pressures of respiration, and we know the 3 gases of respiration. The next concept that really makes this real easy to think about is if I were to look at that muscle of respiration, which I already said was the diaphragm. Just remember that the diaphragm, again, I said, is the agonist or the prime mover for respiration. It's also called the dome-shaped muscle. It's also going to have a nerve supply, the N, or the innervation, equals the phrenic nerves. So, again, if this is my lungs sitting here, inside of the pleural cavities, inside of the thorax, and here's my diaphragm over here. In order for me to get air to come in through the primary bronchus, in order to come in, I'm going to literally have to take this diaphragm and pull it down. So when I contract my diaphragm, contraction of the diaphragm is going to lead to increased. So we're going to increase the volume of the lungs. And at the same time, when we increase the volume of the lungs, we're going to also decrease the pressure in the lungs. So when I pull this diaphragm down or contract it, this is going to cause the lungs to get larger, the pressure is going to go down, air is going to flow in, and that's going to lead to inspiration. Just the opposite of that. Here's my lungs again. The lungs are sitting on top of the diaphragm. But now the diaphragm is going to relax. I've still got my bronchus coming in. So when I relax the diaphragm, or relaxation of the diaphragm, is going to lead to a decreased volume of the lung. It's going to cause an increase in the pressure in the lung. And that's going to lead to expiration. So now we know how air comes into the lung and comes out of the lung by using that principal muscle of respiration that is the one that we use for normal breathing or quiet breathing. The other thing we want to kind of think about is there's several muscles of respiration, so I'm just going to list them so they're very significant to know. Remember, that's going to be the diaphragm, then the external intercostals, then the internal intercostals, then the scalenes, and the serratus, and the levator scapula, and the levator costarum. And then generally I say that also add the SCM, or one you're probably familiar with being the sternocleidomastoid. So this again is going to be, the diaphragm is going to be the principal muscle, or the agonist. And these muscles here all are going to help or assist the diaphragm. So those are going to be synergists. Equal assist. So they're going to assist the agonist. And then one other thing I think that's very significant, because if you're going to healthcare, you're going to be talking about chest tubes and pneumothorax, hemothorax. Think of the external intercostals. I'm just abbreviating inter with intercostals. Remember, the X's are going to be for inspiration, and the internal intercostals are going to be used for expiration. Just remember, X's are in and N's are X. All right, so now that we've got those concepts down, the next thing we want to think about is what happens when we get some type of a trauma or injury. So now we want to think of a couple of terms. Well, we know that there's this term called a pneumothorax. And that uses the acronym of a PTX. There's also the word of a hemothorax. And that uses the acronym HTX. And when you either get a pneumothorax or a hemothorax, it leads to atelectasis. which is a term that just really means collapsed alveoli. And that's going to be an ATX. So just to think of those in a real simple diagram here, let's just review just for a second about the ribs that we have in the body. So here's a rib. Remember, a rib is called a costa. Then I've got a space, and then I have another rib, which is a costa. And then sitting between those two ribs is what's called the intercostal space. And what's significant about the intercostal space is three structures run through the intercostal space. And I always think of my name for the acronym of a V, an A, and an N. So therefore, running in this intercostal space is going to be the intercostal vein, the intercostal artery, and the intercostal nerve. So that's what's running through that space. And again, if you just to refresh your recollection of musculature from 168, when you're looking at that rib cage, and this again is a rib here, so I'll just write costa or rib. And then I'm going to write here another costa. Basically, I've got a series of muscles running in this direction. Those would be the first set, and those are my external intercostals. And then deep to the external, in the opposite direction, running diagonally, are going to be the internal intercostals. Now, if we tie all that together and think about those words pneumothorax, hemothorax, and atelectasis, if someone has a lung, so let's just take this and say we looked at a chest film, and the story is we've got a 40-year-old male that had a stab wound with an ice pick. And when this ice pick came in or entered the chest wall, before it entered, we took an x-ray before the stabbing. And it looked kind of like this. This is a normal chest film. And I can literally see the diaphragm sitting here. I can see my lung sitting here. And I can see my intrapleural space is normal. So the space between the visceral and the parietal pleura is normal. So that's a normal chest film. But now, if I had a chest film after the stabbing or the stab wound, literally the chest film would still have the diaphragm. I would still have the parietal pleura in place. But now, when that ice pick entered here, it caused the lung to collapse. So what happened is atmospheric air pressure entered the intrapleural space. And that led to a pneumothorax. And when you get a pneumothorax, you can see that the lung itself is collapsing, so therefore these alveoli are collapsing, and that leads to atelectasis. So therefore, this again is a PTX, an atelectus collapsed alveoli, or an ATX. So that's a 40-year-old again with a stab wound. Let's think of another example here. Now let's just say it's a 40-year-old female, and let's say she has an airbag deployment. Same thing, when the airbag deploys, it's actually not a penetration unless it's one of these Takeda airbags where the piece of metal went through your chest, but it's just a trauma of the airbag exploding and pushing the chest wall up against your rib cage and naturally up against your lungs. So therefore, same thing, when we think of an airbag deployment, what's going to happen is we're going to say, let's just take a chest film of this 40-year-old female before the airbag deployment. Again, this is a normal x-ray or a normal film. And we can see that the person has a normal intrapleural space. But now the airbag is going to deploy. And when the airbag deploys, now we're going to see that we're still going to have that parietal pleura in place. But now, because of the deployment, it's going to cause pressure to literally cause accumulation of blood. So what's going to happen, it probably won't be as intense looking. We'll have something that looks kind of like this. So if you notice my interpleural space here, instead of being filled with atmospheric air in the pneumothorax, is going to be filled with blood. And that blood is going to lead to an HTX or a hemothorax. So now we just have to think of treatment of this. If we say that we had a PTX again, a PTX, depending on the size of it, in order to get it to resolve, they either would use what's called a dart or a chest tube. So if we said this is treatment, and of course the chest tube means that I'm going to take a chest tube, and so here's again, remember this is my costa or my rib, and then I've got this other rib sitting here below it, so there's my second costa. This is going to be my intercostal space. And then, of course, remember we've got that intercostal vein, artery, nerve running through that intercostal space. But now what I have to do is I've got to somehow evacuate that air. So if this is that air from the pneumothorax, there's my parietal pleura, there's my visceral pleura. I've got to get a chest tube now, and instead of this ice pick that came in here, I'm going to have a chest tube, so that's what literally this is. Now I'm going to attach that to vacuum, and that vacuum is going to evacuate the air with what's called a thoracil, and slowly evacuate that air out of that and literally re-inflate the lung. Now, if it was a hemothorax that we had up here, literally we could probably let that resolve on its own if the bleeding has stopped. If the bleeding has stopped, then we've got to get a chest surgeon in to stop the bleeding. But if the bleeding has stopped, we're just going to kind of watch that and notice we're probably going to have some increased respirations and probably some respiratory issues from that. And eventually that blood pocket will resolve over time. But for a long time period, a person will have a chest film, and if they don't know that the person had a prior hemothorax, he may say, oh, you've got a tumor or some type of growth in there. But actually all it is the blood that certainly hasn't totally dissolved in that over time. So now we know something about the pressures of respiration. We know the gases of respiration. We know a couple pathologies of respiration. And so lastly, the thing we want to just keep in mind is that we've got those definitions that we want to memorize from the book. Remember, we've got something called a TV or a tidal volume. we've got a VC, or the vital capacity. We've got a TLC, or a total lung capacity. We've got an IRV, which is an inspiratory reserve volume. We've got an ERV, which is an expiratory reserve volume. And then, if we kind of think of those numbers, then we've got some air that really never leaves the lung called an RV, or a residual volume. And again, just think of how this really works. But when I'm sitting here breathing normally, it's called a normal breath, or normal breathing, which is called tidal breathing, which is also called eupnea. If I take a tidal inspiration, so if I take a tidal inspiration, or a normal inspiration, as I'm doing right now, and say, I want to take in as much air as I can to fill my lungs up, that's going to be a inspiratory reserve volume. So if I take a tidal inspiration and then take in as much air as possible, and force myself to take in, that's going to be a IRV, an inspiratory reserve volume. How much air I can fill my lungs in after a tidal inspiration. If I did a tidal expiration, same thing. I would force out as much air as possible. And that's going to be an ERV, or an expiratory reserve volume. There's a certain amount of air that never really leaves the lungs, and that's what keeps me from desaturating. You probably have all had a pulse oximeter on your finger. It's usually on your index finger, and they're going to put the pulse oximeter on, and you're going to be measuring it. And if you notice if you were to notice as you take a breath of air, you kind of look what's called a plethysmograph of it. But if we said this was 0, and this was 80, and this was 100%, and that's saturations or sats, and let's just say, does it look like this? So I always say, does the plethysmograph look like this? Which means this is a inspiration, and that's a expiration, and that's an inspiration, and that's an expiration. Or does it really, so if that was diagram A, and this was diagram B, so the same diagram, except in diagram B, if this is 0, and this is 80, and this is 90, well, this is 100 up here, what does that look like? Well, let's just say that it's kind of like this, and then we've got an elevation and down, and an elevation and down, and an elevation and down. So that's going to be an inspiration, expiration, inspiration, expiration. Okay? So just remember, there's your I. And so it looks like this. This is actually how the human body works. It's never like that. So this is the incorrect answer for what a plethysmograph would look like. It actually looks like this. And the reason being is the reason I never desaturate down is because of the RV, that residual volume, that amount of air that never really leaves the lungs actually keeps me from desaturating. So next time you see a patient or yourself with a pulse ox on, you'll notice that as you're inspiring or expiring, it doesn't go from 96 to 80 and then 80 to 96 and back and forth. It always stays pretty much within that 90 to 96% saturation range. So that now takes those figures into play. And of course, this total lung capacity, just always think that total lung capacity is generally going to be greater in females. In males. So men tend to have a much greater, and I'm going to use a number sometimes as great as about 6,000 milliliters of total lung capacity. Whereas a female generally is about 2/3 of that. So I always say that for a female, kind of a number somewhere around 4,000. And it's not just dependent on the size of the person, it's just that the anatomy of the female lends itself to having less of a total lung capacity. The last thing I just want to talk about before I leave the respiratory system is just, again, looking at the gross anatomy of the lung. Remember, this is going to be my right lung, always looking down at the human body as the right side of the body. Remember, this is going to be the apex of the lung, and this is going to be the base of the lung. Remember, sitting at the down here is your diaphragm. Remember that sitting between the lungs is what's called the mediastinum. And that's where I'm going to have my heart. And I'm going to have my great vessels. And I'm going to have my bronchus, my trachea. And I'm also going to have some lymph nodes. And I could go on in here, and the thymus gland, just for examples. But remember, if this is my right lung, and this is my left lung, my right lung is going to have 3 lobes, and my left lung is going to have 2 lobes. Right's going to have an upper, a middle, and a lower. The left is going to have an upper and a lower. The reason being is that the heart, that's why the heart is a little shifted to the left. And so if I draw this heart example here, you'll see that the heart is like this. Remember, the heart is the top of the heart is actually the base of the heart. So if it's talking about the heart, the base is the top of the heart. And then the heart, the apex, is the bottom of the heart. So it's that apex of the heart that fits into this indentation called the cardiac notch. And that's why I only have 2 lobes on the left and 3 lobes on the right.